Okay.
So we all stand now, so let's do some math. Here we go. Okay, so today we're going to look at product patterns. So think where this is. Let's put this in context, right? We've been talking polynomials. Right? Last time we talked about new stuff. A few days back, we talked about what it is to be a polynomial. We talked about how to add, subtract, and multiply polynomials. Well, today we're going to look at some pretty cool stuff. This is, if you're a math person, this is really cool stuff. So let's click them all the way closed, phones away, earbuds away, all that stuff, please. I want your total attention here. You're going to love this. So we're going to look at some types of products we can take with a specific kind of polynomial. We're talking about a binomial. We're going to look at some binomial product patterns. First of all, let's remind ourselves about something that we've mentioned this year, but we haven't really dealt with it in great detail. So we'll kind of come back to it here. Let's get, Chromebooks should all be closed. I want everybody else's attention up here, please. Thank you. So conjugates. What's it mean to be a conjugate? If I've got a binomial, I've got a first term and a second term, right? So if I'm adding those two terms together, like I have something where I've in the form a plus b, where a and b could be whatever. A could be like 3x and b could be 11 or something. Who knows? Then the conjugate of that binomial is going to be the same two terms, but subtracting them instead of adding them. Okay, so in other words, a minus b is the conjugate of a plus b, and a plus b is the conjugate of a minus b. Okay? So what happens when we multiply a conjugate pair together, an a plus b times an a minus b, or vice versa? It makes no difference. I end up getting a squared minus b squared. So we call that a difference of squares. Okay? The product of a conjugate is the difference of the squares of the terms. Okay? So let's look at an example. So what if we had something like, let's say, 2x plus 5 times 2x minus 5. So what's my a and what's my b in that pattern? So you'd include the x. So the a is the 2x, right? So all that stuff is a, 5 is b. So I end up with a plus b times a minus b. And we know that pattern, right? The outcome is just a squared minus b squared. Okay, so we're going to get a squared minus b squared. What's my a again? 2x. And my b? So we just have to simplify that. We're done. So what is, by using our properties of exponents, what is the quantity 2x squared?
4 times x squared.
4 times x squared, because I'm going to square the 2 and square the x, right? So I get 4x squared minus 25. Simple. And so there's one pattern we're going to look at today, the conjugate product pattern. Okay, now we're going to look at some binomial expansion. So what if we've got a binomial to a power? Okay, this can get difficult if you don't know the tricks, right? Like what if we wanted to do a plus b to the fifth? Well, I'll tell you what, just to kind of put this in context, what if we wanted to multiply? I just want to kind of remind you what it means to multiply a bunch of things together. What if I wanted to multiply something like, oh, let's say 2 times 3 times 4 times 5 times 6. Okay, well, how would you do that?
Just 2 times 3.
2 times 3 is 6 times 4 times 5 times 6.
6 times 4, which is 24.
So that's going to be what, 120 times 6, which is 62. Okay. Now those are just numbers, so it's easy, but can you see where that would be kind of tedious if you had binomials that you're trying to multiply out? Right? If I wanted to multiply out a plus b to the fifth, Remember, that is not as simple as a to the fifth plus b to the fifth. It's a plus b times a plus b times a plus b 5 times, right? So if I wanted to do that problem, I would first have to do that problem, and we know that one. That's going to be a plus b times a plus b is a plus b squared, right? We know that one. First part squared plus 2 times the product plus second part squared times a plus b, etc., right? 3 others out there you got to multiply by. Yes, sir.
Why is it instead? When it was even the stuff we just did.
You mean? What do you mean by that? What's that form?
No, why is it in 2a plus 2ab plus b squared?
Well, because I just multiplied those two out, right?
So you just put it into.
I just did that part in my head because you guys know that part, right? You know how to do a plus b squared. That's a pattern we've talked about. It's the first term squared plus 2 times the product plus the second term squared, right? Phone should be away, please. Okay, so look what I'd have to do then. I'd have to take that whole big thing times a plus b. Distribute an a all the way through it, distribute a b all the way through it, add up like terms. Get an answer. That's a little bit of work. Then I've got to take that one and I've got to distribute, I've got to multiply by another a plus b. Distribute the a all the way through, distribute the b all the way through, add up like terms. Simplify everything, right? Do it again. It's a lot of work just to get one product, right? Wouldn't it be nice to have a simple way to do this, a shortcut, right? It'd be a lot easier. Say it again.
Is it triangle?
It's Pascal's triangle. Yeah, Pascal's triangle is what's going to save the day for us. It's going to lead the way.
Well, I don't know about that.
No.
So you're gonna say-
So here's Pascal's triangle. So Pascal's triangle does lots of stuff, but it does something for us today. Now does that look scary?
It looks like he's trying to explain the trickle-down economics.
Trickle-down economics doesn't work. It's impossible to explain because it doesn't work. That's been shown time and time again. Even though we keep trying it doesn't work. So this is really simple to build, right? Simple to build. Pascal's triangle, the rules to build Pascal's triangle are very simple. When you want to move from a row to the row beneath it, all you have to do to populate, we'll call them cells or squares or whatever. I mean, I wouldn't normally write this with squares. You just write the numbers. Okay? Like I would, instead of writing it this way, I would just write it as 1, 1, 1, 1, 2, 1. But either way, the rules are, when you want to come up with a number in a following row, one that's lower than the one above it, you're just going to add up the numbers that are above it, that are immediately above it, right? Well, there's only one number immediately above that 1. It's a 1, so that stays a 1. Same thing there. The slopes of Pascal's triangle, the sides will always just be 1s. They're never going to change because you're only adding up a 1 above it, so they never change. But inside they do. Inside, 1 plus 1 is 2, right? So we get a 2 there. But what am I going to get here? 4. Not 4. I'm only going to add up the 2 above it, so I'm just going to get a 3 and a 3. If I work my way down, this is going to be 4, 6, 4 and 1. Good. And we could keep going.
This is fun.
15, 20,
You already know.
15, 16.
Okay, and it's pretty easy to build. I mean, we could go further. You build it pretty quickly, right? But I want you to notice a couple things. So there are a few things here that if you think about this, it's going to improve your understanding of this relationship. Notice that there is symmetry here about the center of the triangle, right? So in other words, if I look at any one of those rows, forwards or backwards, the sequence is the same. Has to be, right? Everybody get that? Okay. So if I take this row, 1, 4, 6, 4, 1, and read it backwards, same thing. 1, 4, 6, 4, 1, right? Okay, so Pascal's triangle does lots of stuff. Now, it does some kind of cool stuff. So one thing it does, just before we move on, just kind of a fun little thing. If we look at our Fibonacci sequence, right? Remember the Fibonacci sequence we looked at the beginning of the year? Fibonacci sequence, you start with the numbers 0 and 1, and all you do to get another number, just add up the two preceding numbers. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 8 plus 5 is 13, 13 plus 8 is 21, etc. And we keep going, right? That's the Fibonacci sequence. And it's amazing. Those numbers show up everywhere you look. They're just all over the place, right? Say it again.
Rivers.
Rivers,
That would
you look at pine cones, you look at the sunflowers. I mean, it's just no matter if you focus in on anything that has that where you've got you have to have spiral relations. Like if you looked at broccoli under a microscope, you'd see that if you look at broccoli under a microscope, the little buds of broccoli are going to follow the Fibonacci. It just happens everywhere, right? So if you reconfigure Pascal's triangle, so here's what we're going to do to it. If we take Pascal's triangle, we're just going to reconfigure it. So I'm going to drag each of these rows over so that the left side of the triangle is going to be vertical, right? And then the right side is going to be just kind of a longer slope. But we're still going to do it so that we line things up vertically this time. So all the ones would line up vertically. And all of the second numbers would line up vertically. And the third numbers would line up vertically. It would just become that.
That's like how we figure out to fill out electron
Oh.
orbitals. 1 is 2, 2 is 2.
How about
That's so
that?
fun.
Yeah, how about that?
You said that was fun?
Yeah. 1 is 2.
Well, why wouldn't that be fun? I mean, seriously,
Yes,
if
two.
I would say you got a
3p6.
problem in life if you don't think that's fun. If you can't
Yeah.
think that that's fun, then you got to reevaluate your life a little more.
I
because-
stand electron orbital filling up.
Yeah. I mean, humans, you know that the worst thing you can do to a person, what is the worst form of torture? And it's absolutely for sure.
Isolation.
Isolation is the worst form of torture. I mean, I suppose if you're going to gruesomely,
Nah,
you can.
I don't want to talk about it. No
Put
gross.
it on their
No
forehead.
gross.
no, you blind them first. Put them in a dark room, you blindfold them, and you put water.
Well, let's not. I don't want to. I really don't want to talk about ways to damage.
No,
I do want to make this. This has absolutely been shown to be true. If you look at psychologically, prisoners that have been subject to long periods of torture, and if that's where it's not killing them, but they're the thing, regardless of what those have all been over long periods of time, the thing that they dread the most. If you go back and ask them, and this is 100% of the time, they always say the thing that was the worst was isolation. That's just the way, it's the worst thing you can do to a person that psychologically damages a person is by themselves for too long. And it's, in many cases, it's irretrievable. If you put somebody in isolation for an extremely long period of time, it changes their brain in such a way that they don't often even recover. My point is just this, though, that the human brain, why is it so damaging, why is it so psychologically damaging to isolate somebody? Because of the way that our brain has evolved. Our brain is a tool that's evolved to help us deal with, we're not very fast, we're not very strong in the animal kingdom, but we did evolve one thing that allows us,
Prefrontal cortex.
we allowed one remarkable feature that allows us to outcompete every other animal on Earth, and that's our ability to adapt to an environment.
And make guns.
Okay, so,
I could destroy it, brother.
what's that?
I could destroy it.
A gorilla? Well, I
Doubt.
tell you what, you probably couldn't destroy a gorilla, mono in a ring, but if you had resources available to you,
That's what it's.
you could destroy a gorilla because you can use your brain to outsmart the gorilla, right? Not that we ever want to destroy a gorilla.
No.
But
They are
anyway,
endangered.
but we're getting off track here. Let me just reel you back in. So, the point is, and I went off on a tangent here, but it's an important tangent, I think. Sometimes, I hear this kind of stuff where people are like, wow, you want to know everything you can, because that's what the brain does. And you guys are at a point in your lives right now where you'll never get this back. Your brain mass doubles between birth and age 5, and it doubles again between age 5 and about, in college sometime. So you're at the very tail end of the last chance you're gonna get in your life to just learn stuff for free. I mean, your brains are so receptive to learning right now that you would be really dumb not to take advantage of that. If somebody were to say, I'm just gonna drop dollar bills into this room right now, and you have 5 minutes to pick them up, would you wanna wait until 4.5 minutes have passed and then start picking up dollar bills?
Yeah,
I wouldn't.
because then
I would start right now, I'd wanna get as many as I could.
I'd take the money that people would like
right? But you get my point.
Yeah.
Dude, these are not helping right now. Hold your thoughts
There's
for a
always
second.
what ifs that you could apply to situations, but usually by third grade, we realize to stop doing those, because, yeah, we'd often realize
Well,
that.
they're good sometimes, but now's not. So, 'cause I wanna get through some math here. But my point is just that you gotta be, seriously, you gotta be taking advantage of this because it goes away. How many times have you seen people, families that immigrate to the United States and the kids come when they're small? By the time the kids are 18, what do they sound like when they talk? They speak English with no accent, right? But the parents come over when they're adults, and it can be 30 years later, and they got a thick accent. Sometimes they never really are able to speak the language absolutely fluently. How come?
Because they've been, they didn't grow up, they grew up in
Because they grew up with their native language, and here's the critical part. That's not really the issue, because kids can learn multiple languages and speak them all perfectly fluently when they're young. But the brain there is an ability of the brain to adapt. It's called plasticity. Listen, Chromebook's gotta be closed. We don't have time for that now. I don't wanna fight that battle with you guys, but when I'm doing this stuff, if I have to, I don't wanna make you have to put them away every day, but I don't want you guys on the Chromebook, so we're doing this. It's just, I don't wanna ask. There's a certain amount of plasticity associated with the brain. It's why if people become injured, like let's say you go blind at an early age. Is it a myth that your other senses become more acute? It's not. They absolutely do. I dare you to try to read Braille right now. You can't do it. You can't do it because you don't have the ability to do it. Because people that go blind, they're able to, the plasticity in their brain allows them to leverage big volumes of their brain to do things like be able to interpret, read Braille quickly. I'm not gonna say you couldn't do it, but it would be more difficult to do because you're using a huge part of your visual cortex for seeing things, which is important. But if you're blind, you can reuse that. You can reuse that portion of your brain that's your visual cortex for question.
So even when our eyes are closed, we're still seeing something. So what do blind people see?
So I don't know if you can answer that. I mean, I don't know if you, I don't know. But I would guess that what is seeing anyway though?
Yeah.
I mean, seeing is,
Reflection of
because
light.
you get this.
Is a reflection of light to your optic nerve.
Yeah.
It's
Yeah,
only
you guys-
mirage. Everything's an illusion, Connor, nothing's real.
Well, it is. It is. I mean,
Yeah, I know.
it really is. You
Well,
get
think
that when
about
you
it.
see stuff, you're not, people have this idea that what you see is reality, and that's absolutely not the truth. And you gotta remind me, we're gonna be more receptive. Once we're done with the SBAC test, we can kind of wade into some other things here. But you know that eyewitness testimony is one of the most unreliable ways to, it is absolutely not factual.
Yeah, because there could be 5 people that witness the same thing, but each one would have a different story because of the things they experienced.
Absolutely,
Your
right?
brain likes to remap and hide the trauma and make you think you saw something you didn't.
Right, it fills in the blanks.
The
There's,
brain would rather hide behind a comfy lie than face the bloody truth.
okay, there's some truth to that, because your brain has defense mechanisms, psychological defense mechanisms, but even just the physiological process of seeing, that what really happens is there's a ganglial bundle on the back of your retina, and that sort of pre-processes vision, and that does some processing, and then it goes to your brain, and your brain processes the rest. But it's not like it's taking every little conceivable pixel of information and accurately representing it. No, it's taking lots of shortcuts. That's why optical illusions work, right? Because optical illusions play on the fact that your brain has to take some shortcuts to process information with it, so they can trick your brain into constructing false images, right? And so your brain is not by any means giving you a videotape of what you're seeing. It's just an efficient interpretation of the information that's coming in, right? Yeah.
So if you're saying it's kind of like our brain and eyes use shortcuts just for us to see, what if they didn't, and if it was more like efficient or fast or something? Would that mean be able to see like more primary colors,
Is
like
that even
a higher
conceivable?
quality?
Okay, so what it would mean is probably that you would have a bunch of extraneous information that you wouldn't be able to process. Now, you notice that like your fovea centralis, like if you, and we could do a little, try this sometime. If you drop a dot on a piece of paper, and you kind of put it out on the side,
It
and
goes
you move
away.
this thing closer, there's gonna be a point there where it completely goes away, right? You don't even hardly notice it.
Or this thing, when you do like this, but stare, like you can stare at the wall, but do this, your finger looks like there's a middle finger.
Yeah, it is. So there's all these little tricks you can play on yourself. But you don't have visual acuity. I can read those signs right now, but if I look over here, I have no hope of reading them, right? I can't see any detail over on the side of my peripheral vision. How come?
Difficulty in processing.
I know, right there.
Well, do it later. It's fine. Try that stuff later. But how come you don't have visual acuity in the middle? Because you don't need it. It's too much information. Your brain can't process all that accurately, right? Instead, you'd rather have your brain take the task of being able to very quickly and efficiently be able to assemble high detail information in the area of interest and just get an idea when there's big things going on, like the cougar is moving towards me from the side, right? I need to be able to establish that there's some motion there, but I don't really need to be able to tell, is it smiling at me, or is, I mean, I can look over there and see, right? That's why I can turn my neck to do that stuff, right? And so it's it's just an adaptation, right? People have, they've evolved these tendencies to be able to deal with real world issues, and we have central acute vision because that's the most efficient way of using our brain. It takes a lot of brain power to see things, right? The visual cortex is a pretty significant volume of our brain. Yes.
Isn't that why predators usually have their eyes on the front of the head and on the side?
Yes. You'll always see that predators have their eyes on the side, and animals that are preyed on have their eyes, they see, they're able to see things more acutely over a larger area, but they use a lot of their brain power to be able to just not get eaten. Right? Predators are usually going to be smarter than non-predators because of that. They don't have to require slightly.
Chronology.
So,
Pseudo-silent.
okay, I'm getting way off on a huge tangent, and I got to get back to business here. But my point was just, the reason I said this, and I want you guys to think about this, is, you got to feed your brain because your brain wants to be fed. Whether there's, and I know it's easy to get lazy and it's easy to get sucked into things that have very little payoff, but like TV addiction and video game addiction are just, they make total sense if you think about the way people respond to stimuli, visual stimuli. But once again, if you go back to millions of years of the way we've evolved to be able to, for most of our human history, to be able to not die, right? And the creatures that don't die out, until they reproduce, they're gonna pass on those genes. I mean, we don't die because if we see something moving in the bushes, we respond to it and we train our attention on it. And we run away, or we throw a spear, whatever we do, right? But at some point, all of the early creatures that didn't have that ability to respond vigorously to motion got eaten, and they got weeded out, right? So it's just something, you can't fight it. You can't fight it. It's just, it is a part of who we are as humans, that it's deeply ingrained in what we've come to be, that when something is moving, you fix your attention on it, right? Which is why video games and TV and YouTube, all that stuff is so unbelievably addictive, because what's it always doing? It's changing, it's moving. There are things going on, and so you find yourself just doing it, watching it, because it's deeply stimulating to that part of the central brain, which is the part that's the hardest to fight, because it's the part that's involved in survival, right? Okay, but what you want to do instead, as intellectual people, is you want to instead you want to leverage the other part of your brain that's more useful to you, and that is that your brain also wants to know stuff. The brain wants to learn. It's got a thirst for knowledge. It's just part of who we are, right? I mean, things that are new are interesting if you can make them interesting.
And if the church lets you investigate.
Well,
For a while,
we're not touching.
No, like Galileo and stuff, not like.
Okay, we're not touching. Sorry. But, right, I mean, it's, that's the trick. That's the trick in life, is if you can make anything interesting to yourself, your brain will automatically be good at it. Think of the things that you're good at, right? The things that you're good at that are interesting to you. Anybody like snowboarding? Any snowboarders in here, right? Okay, if you like snowboarding,
Yeah.
snowboarding is something that's interesting to you, and you become good at it pretty fast because your brain latches onto that, and it becomes good at something that it focuses its attention on, right? You improve rapidly. So the trick is academically, like when you get to college, you know, if you can, in high school now, if you can just trick yourself into being interested in something, and you can, you really can. I mean, that's something, that's just called, have willpower. That's just being able to have some self-discipline. If you can just take a period of time, you can't do this all day long. You can really focus for short periods of time. But you gotta train yourself to say, okay, now I'm gonna focus, I'm gonna give myself a break here in a little bit, But it's not even in every class can you probably do that, right? Some classes you don't have to as much. Math is one where you do. I mean, math is one where, you're gonna be periods of time where you just gotta go hard for a while and then let your brain relax. Our school system's terrible in many ways. It's just designed, it really is.
Period system.
No, it is. Our school system is designed exactly wrong. Like, if you go to places in the world that are a lot smarter than there, like in Finland, where their high schools are far, far superior to ours. What do they do differently? How many classes a day do they have? They don't have 7. They have 1 or 2 or 3. Do they ever have homework? No, they don't. It's a national policy that there's never any homework. No homework. You go to school and you work hard for a period of time, but then they have built-in adult recess for even like kids that are in high school or college, where you're encouraged to go out and do something that is completely unrelated to what you just did, to relax your brain, right? And then you come back and you get rested, you come back and you're gonna work hard for another short period of time. And then you go have fun. So they literally, they have things where you go out there and they've got a video game station where you're gonna go play video games for a while. That's part of your day because you're supposed to let your brain relax. That's what brain research says.
I'm moving, let's go, Will.
You do puzzles, you go out and you do athletics, you go out and play a game of basketball or something, because that's just what you should do if you're really learning, and that is the truth. If you want to learn effectively, you have to do it in short, intense doses. It's like physical training, right? You don't lift weights all day. You lift weights for a short period of time, really hard, and let your body recover, right? I mean, that's what you do. Your brain's the same exact way. So you just gotta if you know how your brain works, you just use it in the right way. It's much more efficient, right? But you gotta make yourself interested in whatever you're doing. If you found out that you had a week to live, it'd be easy to do. You could go back and think of all those times you took out the garbage that you thought it was terrible. You could probably, if you could gather all those back, you'd probably go do them, right? Because you could find some beauty and value even in taking out the garbage if you didn't have much time left on earth, right? That's the approach you gotta take to everything, and then you just become smart, because your brain becomes interested, and that's how you get smart. Yes, sir.
So basically, you're telling me someone can just go for 2 periods.
No, I'm not. I'm not telling you that. Don't tell your parents I said that.
I'm telling the principal.
You also told us we have to always ask the church before we do stuff. That's kind of weird.
I'm not telling you any of that stuff either. Yes, sir.
But you are saying we need to lie to ourselves in a sense.
I think you do. I think you do. I think in a way you have to just develop the capacity to make yourself interested. But I promise you, as somebody that's older who has done this my whole life, and that's honestly, if I've been academically successful in life, it's been because of this more than anything else. I promise you it is. It's just if you take any situation and if you find yourself spending a little time looking into it, it might have been something that you would have thought would have been worthless before, but just try this, just humor me. You will find very shortly that you kind of find yourself, oh, huh. That's it, well, what about, your brain just does that stuff. It just naturally does that. It's going to start to consider the situation from different points of view, and it's, right, it really does. And so if you can just discipline yourself to focus for a little while, your brain can't help itself. It's going to get interested. It could be whatever the most boring subject for you might be. Maybe for me, it probably would have been history. But I guarantee, if that's the subject I always liked the least. But I always found if I just could, allow myself to get into it a little bit, I don't know if it was interesting. It's still my least favorite, but it could be very interesting, right? Anything can be that way if you just let your brain have a chance. Okay, off my soapbox, we gotta get back to math.
You're preaching.
One more thing.
No more things. Okay, so now let's engage our brains a little bit. So what does this Pascal's triangle do for us, right? We got all these rows in our Pascal's triangle. What are they doing for us? Well, it turns out among the many things that Pascal's triangle does. It's the Fibonacci sequence. It does all kinds of other important sequences in math. They come out of this triangle, which is bizarre. They all come out of a simple little triangle, but they do. But the one that we want to focus on today is just that the numbers in each row are the coefficients that we get when we multiply out binomials to various powers. Okay, so for example, if we assign a row, so let's look at this. We've got the binomial x plus y, simple one, right? So let's just take that to different powers. Like we'll start off going to the 0 power, then the 1 power, then the 2, then the 3, then the 4. Those become the rows in the triangle. So the row 0 is what we get if I take x plus y to the 0. What's anything to the 0?
1.
1. There you go. Simple, right?
1.
X plus y to the 1 is just x plus y, right? So the coefficients are 1x plus 1y, okay? X plus y squared. Go down to the next row. X plus y squared is 1x squared plus 2xy plus 1y squared. What do you know? The numbers in each row of Pascal's triangle become the coefficients. X plus 3 cubed is 1x cubed plus 3x squared y plus 3xy squared plus 1y cubed. It's so simple. Those are the coefficients. It's got to be a quick question because I got to make hay.
So we also have to move the exponents.
Okay, so that's the other part I'm going to talk about. So the other part of Pascal's triangle is just, okay, what happens to the exponents? Well, if it's row 3, for example, notice that the sums of the powers of x and y or a and b or whatever you're going to call it, whatever we're using, right? In this case, it's x plus y instead of a plus b. The sum of the exponents is always going to be 3, right? So it starts off with all of the exponents shifted towards the first term. So I'm going to get an x cubed, but by the time you get to the end of the row, all the exponential weight has shifted to the other one. So it's all with the y. Each step to the right, or each term in the expansion, the x's are going to drop by 1 and the y's increase by 1, but the sum stays the same that way, right? It still adds up to 3. So the x goes from x cubed to x squared to x to the 1 to x to the 0. The y's go from y to the 0 to y to the first to y to the second to y cubed. It's just that simple, right? Pretty cool. But so Pascal's triangle allows us to take a really big shortcut here. The x plus y to the 5th that would have taken a whole page of paper to do previously, there it is, right? The coefficients come from Pascal's triangle and the exponents in easy pattern, right? Okay, so let's try this a couple times. So what if we want to do something like, well, we know a plus b squared, that's just going to be row 2. Coefficients are 1, 2, 1, right? And we're shifting the weight from the a squared all the way over to the b squared incrementally, right? Okay, so there's our pattern. Well, what do we get when we multiply this one out here? So this is, what's my a and what's my b here?
2x is for A, 10 is for B.
So I get 2x plus 10 squared. So 2x is my a, right? So I'm going to get 2x squared plus 2 times 2x is my a, my b is 10, plus 10 squared. Just simplify. No big deal, right? Okay, what if I have a negative? Let's do a negative one because we're running out of time. We'll kind of speed this up a little bit. Okay, what's my a this time?
10x.
So my a is 10x. What's my b? Negative 1. Okay, and we're going to square that whole thing, right? So I know that if I follow that pattern, I'm going to get a squared plus 2 times a times b plus b squared. Well, a is 10x, b is negative 1, right? So if I simplify that, what is the quantity 10x squared?
100x squared.
Okay, I get 10 squared, which is 100, times x squared, good. 2 times 10x is 20x, times negative 1 is negative 20x, and then negative 1 squared is 1. Done. Okay. If I want to do, what about the cubes? Well, if we fill out this next row, it was 1, 3, 3, 1. So there's my 1, 3, 3, 1, right? Let's do something like x minus y. So what's my A? X. And my B is just negative y, isn't it, in this case? And I'm squaring the whole thing, or cubing the whole thing. So I'm just going to follow my pattern, right? Where I've got A is x, B is negative y, and if I simplify that, I'm going to get x cubed. 3 times x squared times negative y is minus 3x squared y. 3 times x times, what's negative y squared?
1.
It's negative 1 squared, which is 1, times y squared, so just y squared, right? So that's going to be plus 3xy squared, and then negative y cubed is going to be negative y times negative y is y squared, times negative y is negative y cubed, right? The moral of the story is if I take a negative quantity, or a negative number or a negative variable to an odd power, I'm always going to get a negative result, right? Okay? All that happened there is I got a negative term there and a negative term there because I had a negative number to an odd power. Otherwise, I get, when I have a negative number to an even power, it's always positive anyway, right? Okay, one more. How about that guy? We're done. You want to follow? So you got to remember my pattern here, though, right? What's A plus B cubed? What was that one? 1A cubed plus 3A squared B plus 3AB squared plus. There you go, right? So our A this time is what?
10x.
So 10x and negative 9. Good, so we end up with, here's my template, right? A cubed plus 3A squared B plus 3A B squared plus B cubed. Plug them in. That's a 10x. That's a 10x. That's a 10x, because that's an A cubed, an A squared, and an A. That's a negative 9, negative 9, and a negative 9, right? Following my pattern, just simplify. 10x cubed is what?
1000x cubed.
Yeah, 10 cubed is 1,000, and there's my x cubed. Let's see here, I've got 3 times negative 9 is negative 27, right? 10 squared is 100, so negative 27 times 100 is negative 2700, and then I've got an x squared, right? Because I'm squaring the x. Let's see, here I've got negative 9 squared is what? 81 times 3, that's 243, times 10. I just add a 0, right? And there's my x. And then negative 9 cubed, well, negative 9 times negative 9 is 81, times negative 9 is what? What's that? 729. Okay. That's it. You get the idea?
Yes.
Okay, so, you know, it's pretty easy to build, right? There's a limit to how far you want to go with this because it takes time. Like if you had to expand A plus B to the 101st, well, you would want to build Pascal structure. Then you'd use the binomial expansion. For small powers, it's always all you do. That's pretty useful.
During advisory, will be your class picture. So everybody come to Warburg Court during advisory on Thursday for your class picture.
Instead of about trying to figure out the pattern.
It's